Okay, this is our first screencast for Guidesheet number 4, Newton's second law of motion. We're talking about the law of acceleration. So again, Newton's law of acceleration states that the acceleration, which again is the rate of change of velocity, it's not how fast you're going, it's whether you're going to be getting faster, getting slower, or changing your direction. It's directly proportional to the net force. So if we increase the net force, we increase the acceleration. And it's not the force, there's not a single force, it is the overall net force when we have summed all of the other forces, all of the forces on the object together. At the same time, it's also inversely proportional to the mass of the object. So objects with more mass, which on the Earth will equate to more weight, weight being a force, mass being the amount of matter of the object, will need more force to make them accelerate at a higher rate. So more mass, harder to accelerate, larger force, more acceleration. Okay, so in number 1, the acceleration of an object is, again, directly related to the net force upon it and inversely related to the mass of the object. So that would be letter A. In an equation form, we can write that as A, acceleration, which is a vector, equals the net force divided by the mass of the object. Force is also a vector, so direction does matter in both of these cases. More commonly, it's written as F net equals mass times acceleration. And F net is often written as what it stands for, which is really the sigma, the summation of force. So add all the forces together on an object, and that will determine the acceleration of the object, which will also in part be determined by the mass of the object. Okay, so we're just going to predict some effects using this second law, the law of acceleration, for number 2 here. An object is accelerating at a rate of 8 meters per second when it suddenly has the net force increased by a factor of 2. Now, since force is directly proportional, we would expect the acceleration rate to double, and it would become 16 meters per second. Now, we didn't change the mass, so it's just the only impact there was the force, which again is directly proportional. Object accelerating at a rate of 8 meters per second when it suddenly has the net force increased by a factor of 4. So now we would expect it would be 4 times more acceleration because it is directly proportional, and we'd be up to 32. And again, that's not how fast we're going, but for every second that we travel, we're going to increase or decrease our velocity rate, our magnitude, by 32 meters per second. Is accelerating in letter C at 8 meters per second squared. Suddenly has a net force decreased by a factor of 2. Now, since it's directly proportional, if the force goes down, the acceleration magnitude will also go down. If we decrease by 2, then the acceleration also goes from 8 to 4. Just divide the 8 by 2. In D, it's 8, and we increase the mass by 2. Now, mass is inversely proportional. So if we increase the mass by 2, we would expect the acceleration rate to become half as much, the opposite. Increase mass, decrease the acceleration rate. In E, it's 8 meters per second again, and the mass is decreased by 4. Now, decreasing the mass is going to increase the acceleration, and it will do so directly, so by a factor of 4. So 8 times 4, we're going to go to 32 meters per second for every second that we travel. Letter F, accelerating at a rate of 8 when it suddenly has a net force increased by a factor of 2 and the mass decreased by a factor of 4. Now, increasing the force is going to make it times 2 more, and then decreasing the mass is going to make the acceleration go up, be increased, it's inverse again, by a factor of 4. So that's also going to be 4 times bigger. So the overall impact is 8 times more. So 8 times 8 would be 64 meters per second per second. An 8-time fold increase in the acceleration. In G, it's accelerating at 8. Suddenly the net force is increased by a factor of 4. So the force is going to make us go up by 4. And the mass is increased by a factor of 2. Now, increasing the mass is going to decrease our overall acceleration value. So we're going to go up by 4, but down by 2. That's an overall impact of 2 times more. 8 times 2 would be 16. Letter H, an object accelerating at a rate of 8 meters per second when suddenly has a net force increased by a factor of 3, and then the mass is decreased by a factor of 4. So 8 is our start point, 8 meters per second. We're going to increase that by 3 from the force, so now we're up to 24. Okay, and then we're looking at the mass impact. The mass is decreased. It's inversely proportional, so it's going to increase our acceleration by a factor of 4. So we're at 24 times 4 more for the change of the mass, and that's going to make us 96 meters per second. That's about 10 times the acceleration due to gravity. That's a pretty significant amount of acceleration. Okay, and finally, we're looking at these 4 diagrams in the bottom part of the page here. They depict the different forces that might be acting on the object. In each case, the down force would be the force of gravity. And we want to rank these objects in order of their acceleration. So we want to look for the largest net force would have the largest amount of acceleration. The least amount of net force would have the least amount of acceleration. And that would go on the right, and the largest would go on the left. So this one here, this is what we call balanced forces. The total net force is 0. So that's going to have to be our least. We can't get any less acceleration than 0. Negative acceleration is not less than 0. It's in a different direction than positive. This one, the balances, these two cancel each other out. 40 minus 30, this has a net force of 30. This one is 30 minus 15. This has a net force of 15 newtons. The 15 again cancel out. And this one is 20. So this has a net force of negative 20 newtons. Now again, the negative sign here doesn't make it less. It just tells us the direction. So it's the magnitudes we want to look at. The largest one, 30 newtons, is C. 20 is the next largest, that's A. And then the last one is 15. So that's object D. So it ranks in the order of largest is C, and the lowest is B. Now, that makes the assumption that all of the masses are the same. If the masses were different, we can tell the masses are the same because the force of gravity is all the same. If the masses had been different, we would then have to rethink our ranking. But since they're all the same, all we have to do is look at the net force. In fact, you should by now be able to tell that the mass is going to be equal to the force in newtons, force of gravity, divided by the factor for the Earth, which is around 10 newtons for every kilogram. So each of these has a mass of approximately 5 kilograms. And again, that's a measure of the amount of matter, not the size and not the force. All right, that finishes guide sheet number 4. We'll move on and look at using F equals ma a little more detail in our next episode.